So welcome back to the Robotics Lab. Today we're going to talk about our Tormach CNC machine here. I'm really excited about having this in the lab for a couple reasons. One, when we build our circuit boards, we should be able to lay out the circuit in a tool like EagleCAD, translate it into the numerical control codes for this machine, and mill the circuit boards on the machine instead of just hand wiring. And the other thing is, I think it's good to have it in here because as robotics engineers, you're going to be very likely working in an industrial setting. You're going to be working on various computer numerically controlled machines, more sophisticated setups than this. But nonetheless, understanding this machine, understanding the codes, understanding the processes will help us a lot. Because what I've seen as an engineer is a lot of times you'll get a drawing for a part and it may be a perfectly nice looking drawing and everything works in the drawing, but when you go to build it in a production setting or even a prototype setting, there are features in that drawing that make the part difficult to build and more expensive. So the better you understand the machine processes and the things machines can and can't do, the better the parts you're going to design when it comes time to designing parts on your own. Okay? So let's start out. The most important thing here is safety, right? And the key to safety is respect. R-E-S-P-E-C-T, find out what it means to me. R-E-S-P-E-C-T. Okay? You get that? You got to respect the machine, you got to respect yourself. The machine doesn't know where you're at, the machine doesn't know where fixtures are at, like the vise or the table. If your body is in here and the machine makes a rapid move and your body or body part is in the way, it doesn't care. It really doesn't know. It's not that it's mean, it just doesn't know any better. And if the spindle is spinning and you've got your hand here and it does a rapid traverse down, it'll quite happily drill through your hand, okay? We don't want that. That's a real problem for a number of reasons. Reason number one, you're going to get blood in my coolant, and once you get blood in the coolant, I'm going to have to flush it out. That's a big job. I don't want to have to do that. I'm going to have to do paperwork, and your mom is going to be mad at me. I do not want your mom mad at me, okay? So we respect the machine, we respect the fact that it can move suddenly, quickly, and unexpectedly, and we don't have our body in here when the machine is running and enabled, okay? The other thing is, this machine isn't cheap, and it's not cheap to fix, and we need to respect the machine itself. There's a lot of things we can do, a lot of things can go wrong to damage the machine. When we're drilling, we could drill into our vise. We don't want to do that. We could damage the surface. I want to point out one thing. This surface here is a precision ground, very precise, nice, flat surface. And it's great. I can mount my vise to it and I know my vise is flat. I can clamp a part to it, I know it's flat. But if I ding this up, if I drill into it, if I hit it with something metallic and put dents in it, you get raised metal around the dent. Now it's no longer flat. I can't clamp the vise down to it and be confident. I can't clamp a part to it and be confident. We respect these machine surfaces. We have a tool tray over here. When we need to put a tool down, we put the tool in the tool tray. We do not put a tool on our ground surface, okay? Ground surface, tool tray. Tool tray, okay? Put the tools over there, that's what it's for. Behind these bellows here are precision ground ways and gibs. Those are, again, very expensive, very precision. They are covered by these bellows, that's a good thing, but they're very expensive and very precise, and we want to be careful with those, and we don't want to do things that are going to overload those or damage things. And we just generally need to respect the machine, treat it with care. It's your friend, okay? Now let's go over some of the controls. I have up here, I have an emergency stop. At any point in time, I push this, it shuts down the spindle, it shuts down the movement, okay? I can run it in manual mode. Let me release that, push start, turn it on. And I also have to, this light is on, I have to hit the reset here on the computer that's controlling it. Now the machine is all enabled. I can run it in manual mode. I can switch the spindle control to manual. Once it's in manual, I can start it, and it will come up to speed. I can change the speed. I can stop it. I can use the keyboard here to move the table up and down, back and forth. And I got a couple different speeds using a combination of arrow keys and shift keys. I can move it rapidly or slowly. The spindle goes up and down with the page up, page down. And again, with the shift key, I can move it up and down quickly, which brings me to another item of respect. If I bring it down at that high speed into a solid surface, whether it's a fixture, the table, or a workpiece, something's going to give. Okay? That's not a good thing. You know, don't be that guy. Because if you're lucky, you'll break the drill or break the tool that's in here. If you're not lucky, we could break something else and do more damage. So I can use this machine, and I also have a pendant here that I can pick an axis, say Z, and I can move it up. And there's about 3 or 4 different speeds depending on how far I turn that dial. And I can move it down, obviously, and I can jog it by individual steps, and I can pick the step size. If I push this step here, I don't know if you can get this on both on the same camera, it says I'm at half a thousandth here. I push it now, one step is 10 thousandths, or 1,000, 2 thousandths, 5 thousandths, 10 thousandths, 20 thousandths, 10 thousandths again, 50, and right now I'm at that half a thousandth. A thousandth being, for those of you who, 0.001 inches, okay? I've never worked with metric machinists, so I don't know what their favorite term is, but if you work with a machinist in US inch units, you'll hear the word thousandth all the time. You know, instead of saying a tenth of an inch, they'll tell you it's 100 thousandths, you know, or I want 250 thousandths. Well, that's a quarter of an inch. So get used to that term thousandths and multiples of thousandths as a measurement. And because you'll hear that on the factory floor. And those of you who work in a metric or end up in a metric world, put a comment down below and tell me what the metric equivalent to a thou is. Okay, so that's the basic machine. We have coolant, we can run it automatically, we can turn it off, we can turn it on manually. And the coolant we'll talk about later. I'll leave that on auto. Start up and shut down. The computer goes on first, and then we enable the machine. Shutting down, we shut the machine down through the e-stop, and then we can shut down our computer. We do not want to have the machine running and this shut down because it shouldn't do anything, but I can't guarantee it. Okay? So generally, this has to be on first and off last. This is the main thing that needs to be on. So let's turn this on. When I turn the machine on, it's lost. It doesn't know where it is. It uses stepper motors and counts steps as it moves up and down. It doesn't have actual position encoders on any of these axes. So the first thing we have to do, we'll hit the reset here to get everything set and ready. And we need to reference the axes so the machine knows where it's at in machine coordinates. So I'll click reference all. It'll take the z-axis up until it hits the stop and bring it down a little bit. Does the y-axis and then the x-axis. And it just pushes the screen out of the way. That's no big deal. It slides the table over there. Now the machine is at 0, 0, 0 in machine coordinates, okay? And you notice as it's moving, you know, there's not a lot of room, like right down in here. If you're casually leaning here while it was moving, guess what? You know, it's going to squish your hand. Again, the machine doesn't know you're there, so be careful of that. Okay, so it's off in a corner in machine coordinates, but to use it, we'll have to put it in a place where we know coordinates relative to our part. So that brings up the question of, well, how do I put a part in this machine? I have a piece of stock, I want to machine it, what do I do? So let's say we have a piece of aluminum, a fairly random piece of aluminum, and I want to cut another pocket just like this in it, okay? Somehow I have to attach this to this, right? There's a couple ways I can do this. I can bolt it down directly to the table here, okay, using toe clamps. And what I'll typically do is, okay, delay of game here while I get organized. There's T-nuts. You can see the shape of them. And they slide into these tracks. And I can screw a stud into those. No. You need to sing the song from Jeopardy, right? And the clamp itself fits over that, and I have a block that I can put behind it there. I don't know if you can see that or not, but they're serrated, and you can see that they match, and I can mount these at different heights, okay? So if I set the toe clamp here, put the block behind it so that the edge of this is down firmly, it's almost level. Bring this down, tighten it up, and I'll tighten it up, and it'll mount that quite nicely. And I can put another toe clamp on this side. Once I've got two clamps on it, it's not going anywhere. That works fine for something like this where I'm machining a pocket, or if I have, say, a large piece like this, I could mount it directly to the table and machine all I want up on this surface without risk of damaging the table. But if I wanted to drill a bunch of holes in this with it mounted to the table like this, there's a problem, right? And the problem would be, as the drill breaks through, I'm going to drill into my precision ground surface. And of course the first student that does that is likely to fail this class, right? Is that fair? Okay. You probably won't fail the class, but I will not be happy. Trust me, I will not be happy if that happens. I'm not going to say when. I'm going to say if. Okay? And I'll take these out, and I'm not going to set things on my precision surface that I don't need to set there. This is out on this sheet metal apron. That's not a big deal. The other way to do it is to mount something in a vise. If I just put this in the vise and try to tighten it up, it's all cattywampus and nothing's going to work right. So I want to make sure that this is straight. Well, the first thing to make sure it's straight is I need to know that the vise is straight. And what I've done is I've taken my dial indicator, and I'll bring it in here. And if you look at that dial, it's got this little lever, and as you move that lever, and I'm moving it just as little as I can, it spins around, and it gives me a very sensitive measure of displacement here, okay? So I've got this dial indicator. It's attached to the spindle assembly. I can bring it down, and I'm going to bring it down to touch that surface there. Okay, so now as I bring the vise out, I move it in on the vise, you can see it moving that needle, okay? And I can set this, well, it's already pretty close to 0. And unfortunately, just a little bit of jiggling, and okay. So there, it's set to 0. It's touching this back surface. It was set to 0 until I bumped into it. It's touching that back surface, and as I move the vise underneath it, it should stay at about the same position as far as, it moved a little bit right initially because I had some slack in the system. So let's move it over. But as I move it across, you can see that needle is not moving. By the time I get to the other end, it's going to move, like 1/1000th of an inch, maybe half a thousandth. That's pretty good. I didn't know I had it that good. But you can see that this surface here is aligned with the axis of movement. If that vise was cocked a little bit, you'd see that needle slowly sweeping across the surface, okay? So at this point we have confidence that we have a vise that's square to the axis of travels, and we know that it's level because it's tightly down on this surface, and this surface is level. I checked that. I can take apart, and again, if I just put it in here and just kind of cram it, if I put it all the way down, I can't drill through it because I'll drill into my vise, another thing that you will not be doing. If I just try to put it in here, that's hard to do. But so to make sure that this is right, I have some Brown and Sharp ultra precision ground parallels. Okay, you want to be nice to these too. You don't want to drill into them. This one's got a little nick on the edge. It's not perfect. But I can set one in the front, one in the back, and now when I set my plate in here, I know that that plate is flat. It's horizontal, so I can tighten this up. The tool comes out of the tool tray. We tighten the vise. The tool goes back in the tool tray. So now I have my material here. It's flat. It's parallel. Okay, so I've got it in a good position. And now I can start thinking about, well, there's one more step, and then I can start thinking about machining. What I don't know is where it is this way or this way, okay?